For the second part of this tutorial, we will use an image of Saturn's moon Titan from the Cassini mission. We can just use the same notebook as before. We start by loading the FITS file of Titan and taking a first look at the info. Unlike the Galileo image, the data is already stored as floating point values, so we don't need any type conversion. We'll also skip the normalization for the moment. Let's plot the original image first. We'll use an approximate pixel scale of 1.24 arcseconds per pixel, which is obtained from the camera's pixel size and focal length. When we display the image, it appears empty. To understand why, let's have a look at the image statistics by printing the minimum, maximum, median and mean pixel values. Immediately, the problem becomes apparent. The maximum pixel values are several orders of magnitude larger than the typical signal, and the mean is much higher than the median. This tells us that a relatively small number of extremely bright pixels are dominating the intensity scaling. Let us open the image in my FITS viewer to see what is causing this behavior. It already takes some adjustment to make Titan visible, and once it is, we can identify several hot pixels scattered across the image. To reduce their influence, we'll clip the image using percentile limits. We use the second and the 99.9th percentiles of the pixel values as the lower and upper clipping limits, suppressing the extreme outliers while leaving the underlying image largely unchanged. Afterwards, we normalize the image. The statistics now look much more reasonable, and plotting the image again finally reveals Titan with good contrast. Now we will prepare the image for ScopeSim. Just like in part 1, the main thing to do is to determine the angular pixel scale as it would appear from Earth. This time, however, neither the FITS header nor the label file provides the image scale directly. Instead, we derive it from the instrument specifications of the Cassini Narrow Angle Camera. Using the pixel size together with the focal length, we first calculate the camera's angular pixel scale as seen from the spacecraft. Combining this with Cassini's distance to Titan allows us to calculate the physical image scale in kilometers per pixel. Finally, we calculate the angular size that this same physical sampling would have at Titan's approximate distance from Earth, giving us the Earth-based angular pixel scale that becomes our c-delt value. The header update is identical to the I/O example, so we just execute this cell. The source configuration is slightly different. Titan is fainter than I/O, around 8.5 magnitudes, and since it's already centered in the image, no positional shift is required. We'll also disable the neutral density filter and instead shorten the exposure time to keep the detector below saturation. With everything prepared, we can run the simulation and do a quick visual check. And there we go. I hope you found this tutorial helpful, and I'll see you next time.